Hi, it's Moser with a quick tutorial on periodic trends, part 2. Now we're talking about ionization energy. After you've watched this video, you should be able to correctly define ionization energy, as well as be able to use the trends that we see in ionization energy to predict the behavior of atoms, and you should be able to explain the underlying relationship between the trends we see in ionization energy and atomic radius. Well, that means you already need to know all about electron arrangement, and you also need to be familiar with what atomic radius is and the trends that we see periodically in atomic radius and reactivity. So, what's the big difference here? Well, here I have a lithium atom, and it's got 3 protons and it's got 3 neutrons. And here I have something that's marked as lithium 1+. And while it's got 3 protons, it's only got 2 electrons, which means that it has an overall 1+ charge. Well, that's the difference. One of them has lost an electron and therefore is now charged. What do we call this? An ion. An ion is an atom that has become charged through either losing or gaining electrons, creating an imbalance between the number of protons and electrons. So, hey, meet the lithium ion. Pretty cool, huh? Why would lithium do a thing like that? Peer pressure. Totally peer pressure. No, it's not really peer pressure. But lithium would give up 1 electron on its uppermost occupied main energy level because by doing so, hey, it ends up with the same electron configuration as helium, a noble gas. And everybody wants to be like a noble gas. Come on. Well, the process of making an ion is called ionization. And please correct the typo in my notes. Energy is required to make an ion from a neutral atom. So remember, we've talked a little bit about how electrons are lazy, atoms are lazy. Everything in the universe wants to take the lowest energy route possible. But energy kind of changes hands whenever we change up an atom. So whether we're going to add an electron or remove an electron, it's going to take energy. Now, we're going to start off talking about making positive ions. So that's what we just saw with lithium. We remove an electron. Now there are more protons than electrons, and so the ion has a positive charge. The element plus some amount of energy yields the ion of that element and a free electron. The energy change that goes on when we talk about making a positive ion, in other words, the energy needed to remove an electron, is called ionization energy. Hey, isn't that what this video is all about? Oh. So we're going to look at trends in ionization energy, and I've brought along our old friends, the second period main group elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, all the way over to neon. Neon, the noble gas. So, this video is called Periodic Trends in Ionization Energy, so you might think that there are some trends in ionization energy. Well, in fact, there are. And we're going to start off talking about trends in periods. As we go across the periodic table, and we always go left to right, just like we read, we see some trends in ionization energy. And I want you to ask yourself real quickly what you know happens as we go from lithium to neon. You can pause if you need to. Yeah, the atoms get smaller, the atomic radius decreases, and we end up with more and more and more electrons on that uppermost occupied main energy level. Every time we move over one, we add an electron to the uppermost occupied main energy level, which we said in the last video essentially allows the nucleus to have more points to pull on in the uppermost level, therefore pulling all those upper electrons in more closely. Well, you might think that if the nucleus is able to exert a stronger pull on those upper electrons, it would take more energy to rip them away. The better a grip the nucleus has on the electrons on the uppermost occupied main energy level, the more energy it's going to take to pull them away from the atom. And in fact, if we go all the way to the punchline, ionization energy tends to increase as we go across a period in the main group elements. Now, the alkali metals, group 1, give up valence electrons very, very easily. They have the lowest ionization energy in their period across the board. Well, let's look at why. We said of lithium that by giving up one valence electron, it now has a noble gas configuration. Well, the same is true for all of the group 1 metals. So by giving up one electron, sodium can look like neon. By giving up one electron, potassium can look like argon. By giving up one electron, rubidium can look like krypton. So it's not only the fact that there's only one valence electron up there, there aren't a whole lot of points for the nucleus to pull on. Giving up one electron is pretty attractive because suddenly you have a nice, stable, noble gas configuration. As you might expect, beryllium has a slightly higher ionization energy. Boron, slightly higher again. Well, let me ask you this. What do you think? What do you suppose might be true of these guys over here? Well, we're in the P block. We know that. And look at how many electrons on that upper level nitrogen would have to get rid of to look like helium. 1, 2, 3, 4, 5. That's a lot of energy. And what about oxygen? 6, fluorine, 7. They have much higher ionization energies. And as a matter of fact, as you might guess, fluorine, every halogen, has the second highest ionization energy in each period. So the halogens are really not willing to give up an electron because if they gain an electron, then they have a noble gas configuration, and it's only one electron. The highest ionization energy in each period, of course, belongs to the noble gases. When you're perfect, you don't mess with anything. So again, in general, IE tends to increase as we go across a period in the main group elements. Great. Woohoo! Looky here. Well, the blue line up here is ionization energy. And you can see we start off with the first period. There's hydrogen, and we have a big spike. Helium's not going to give up an electron. It's got a noble gas configuration. Ionization energy drops dramatically when we get to lithium. And we have a few hiccups here and there, but in general, the lowest ionization energy in each period is the alkali metal, and the highest is the noble gas. That's neon. Then we drop back down to sodium, and a few hiccups and misorderings here and there. We end up with another spike at argon. We drop to potassium. I hope you have a periodic table out. A few more hiccups and step ladders. We have a spike at krypton. We drop to rubidium and go all the way up to xenon, and we don't go beyond xenon in this chart. Here's what I want to draw your attention to. Look at this other line down at the bottom. It seems like every time the ionization energy tanks, gets really low, this other line is at its highest. Look, there's a peak here, and a peak here, a peak here, a peak there, and everywhere that ionization energy is high, or is low, is high, there's a dip in the other line. What the heck? It's like they're mirror images. Huh, that's peculiar. Well, it's not actually peculiar at all. If we think about it carefully, the reason that atomic radii tend to decrease as we go across a period in the main group, from, for instance, lithium to fluorine, is because the nucleus is able to exert a stronger pull on those outer shell electrons. Well, the stronger the pull the nucleus can exert, the more energy it's going to take to pull those electrons away. So the fact that there are no additional energy levels, no electron shielding, tells us that it's perfectly natural that as atomic radius decreases, ionization energy increases. That's all this chart is showing, is that as atomic radius decreases, as the atoms get smaller, the energy required to remove an upper shell electron increases. It's an inverse relationship, so as long as you can remember that it's an inverse relationship, and you can remember the way one of them works on the periodic table, you've got them both. So let's talk a little bit about removing a second electron. So this is beryllium, right there, and in order to have a noble gas configuration, beryllium would have to lose 2 electrons. Okay. We said it takes energy to remove an electron. Do you think it takes more or less energy to remove a second electron? Well, at the point when we take the first electron off of beryllium, we have 4 protons in the nucleus exerting a pulling force, an attractive force on 4 electrons. And even though those outer shells aren't terribly well held, and they're pretty easy to get rid of, to pull away, it's still an even tug of war here. Once beryllium loses its first electron and we have a beryllium 1+ ion, well, we now have 4 protons exerting a pulling force on just 3 electrons. It's not a fair fight anymore. And in fact, the second ionization energy, the energy required to remove yet another electron, is much higher in elements. Now, once you get to the noble gas configuration, there's no way you're getting another electron off of there. Those are very, very stable ions. And as a result, the energy required to remove an electron from an ion that's at a stable configuration is astronomically higher. So to recap, every time you take off an electron, it gets harder to remove the next one. Because you're removing an electron from a positive ion. Not a fair fight at all. And when you get to noble gas configuration, IE goes right off the charts. It's really, really high. So now let's take a quick look at our group 1 friends. We're going down the line: lithium, sodium, potassium. What do you notice about radius? Well, we know that atomic radius increases as we go down a group, due largely to electron shielding, the addition of extra electrons and extra main energy levels that shield those outer electrons from the attractive force pulling them towards the nucleus. Well, in periods we said that as atomic radius increases or decreases, ionization energy increases. It's an inverse relationship. What would you guess about ionization energy in groups? If you said that ionization energy decreases as we go down a group, you'd be right. It's the same inverse relationship we see across periods. This electron doesn't have a whole lot of shielding between it and the nucleus. And, group 1 gives up electrons pretty easily, but it takes even less energy to get this outer shell electron from sodium because there's just more in the way. It's got 2 full main energy levels between the nucleus and the attractive force of the nucleus and that outer shell electron. Let's not even talk about potassium. Well, potassium's outer electron is shielded by 3 full layers. It's at a great distance from the nucleus. It's really easy to pull off. And as we go down further, cesium and rubidium become insanely difficult to remove an electron from. They have very, very low ionization energies. Which is what we say here. As we go down a group, ionization energy tends to decrease. And again, if you can remember that atomic radius increases, you've really got the battle won. The electrons as we go down a group are in higher energy levels, they're out further from the nucleus, and they're just easier to pluck off. That's it. The big thing to remember is that ionization energy is the energy required to remove an electron from an atom, and that every time you see an increase in atomic radius, you tend to see a decrease in ionization energy, and vice versa. Okay, off with you.